Hi, in this video we are going to talk about the Hall effect, the Van der Pauw method, and the IV curves. This is the course of nanotechnology, and the team is confirmed by Luis Alonso Garcia Insulza and by me, Adolfo Venegas Barajas. First, the definition of the technique. The Hall effect is established by the following procedure. The material to be investigated through which an electric current is passed. The electric current in this image is the red line that goes through the material, and this current is is perpendicular to an magnetic field applied by a magnet, and this causes that the charge carriers to accumulate in a certain place, generating an electric field. By measuring the potential difference in the two surfaces of the material, it is possible to deduce the sign and the density of the change carriers, presenting an linearity between the magnetic field and the Hall resistance. Using a method, we can determine the properties um, of the material that is being measured. And the theoretical foundation. The Hall effect on the conductor is well known. If an electric current I flows through a rectangular conductive sheet of thickness d, and if this conductor is situated within a magnetic field B applied outside the plane of the sheet, the Lorentz force acts on the load carrier of the conductor, where B is the speed that derives from the current and cube the value of the charge. Charge carriers are free particles, mobile and unlinked, carrying an electric charge. For example, the electrons. The Then the system component and technical characteristics. The following figures shows schematically the measurement system. Uh, it this material has to be a conductor, and it has to be rectangular, and it has to be flat. Then the explanation of the values obtained. This this force causes the load carriers to accumulate in the upper or lower region of the conductor according to the direction of the current and the applied field. So that voltage, the so-called Hall voltage UH, appears between 2 points located on either side of the sheet. What is the Hall coefficient? The coefficient of Hall and its sign in turn depend on the density of the load carrier and the type of the charge carriers. On the other hand, this effect makes the resistance measured in the presence of a magnetic field like the one indicated greater than without it, phenomenon known as magnetoresistance. The result analysis. From the Hall resistance, you get a lot of information. For a doped semiconductor that is in the extrinsic or saturation regime, you can find the sink of the carrier based on the sink of the Hall coefficient, the latter being convenient definite. The concentration of carriers and the mobility of the carriers. And the application of this method, under this effect, the sensor hub was created which can be used to measurement of magnetic fields, signal transmitter without contact, and RPM measurement of motors. There is a device called electrometer with which it is also possible to measure the resistance of material, being able to measure very high resistance up to 10 to 16 ohms, so you can measure big values of resistance. The IV curves. It is the presentation of the behavior of V versus I for a given material when solid or liquid conductors are studied at constant temperature. This characteristic curve turned out to be a straight line by the Ohm's law, so they are called ohmic or linear conductors. Otherwise, the material is called non-linear conductor. There are conductive materials in which if its temperature is increasing, its resistance in general increases. Then for a same voltage applied, the intensity will decrease. The suppose or the suppose deviation of the real curve with respect to the theoretical one as shown in the figure. Therefore, an experimental detail must be taken into account when making measurement for materials whose resistance is very sensitive to temperature. When intensity is passing through it, the material is heated by Joule effect, and its resistance will be varying according, so that for a same voltage applied, the intensity will be different from that will correspond if the temperature remains constant. The measurement in this case must be carried out quickly to avoid the variation of the resistance with the temperature.
Van der Pauw is a technique commonly used to measure the resistivity and the Hall coefficient of a sample. Its power lies on its ability to correctly measure the property of the sample of an arbitrary shape, as long as the sample is approximately two-dimensional, solid, and the electrodes are placed on this perimeter. The Van der Pauw method employs a 4-point probe based around the perimeter of sample, in contrast to the linear 4-point probe. This allows the Van der Pauw method to provide an average resistivity of the sample, whereas a linear array provides the resistivity in the same direction. This difference becomes important for anisotropy materials, which can be properly measured using the Montgomery method and the extension of the Van der Pauw method. From the measurements made, the following property of the material can be calculated. The resistivity of material, the doping type, whether it's a p-type or n-type material, the sheet carrier density of majority carrier. This is the number of majority carriers per unit area. From this chart, density of doping level can be found, and the mobility of the majority carrier. Theoretical foundation and conditions. The method was first proposed by Leo G. van der Pauw in 1958. Van der Pauw found a method to determine the resistivity of an arbitrary shaped sample subject to the following conditions. There are 5 conditions that must be satisfied to use this technique. Number 1. The sample must have flat shape of uniform thickness. Number 2. The sample must not have any solid holes. Number 3. The sample must be homogeneous and isotropic. Number 4. All 4 contacts must be located at the edge of the sample. And number 5. The area of the contact of any individual contact should be at least an order of magnitude smaller than the area of the entire sample. System components and technical characteristics. In order to use the van der Pol method, the sample thickness must be such less than the width and the length of the sample. In order to reduce errors in the calculations, it is preferable that the sample be symmetrical. There must be as low and isolate holes within the sample. The measurement requires that 4 ohmic contacts be placed on the sample. Certain conditions for the places need to meet. They must be a boundary at the sample or as close as is possible. They must be infinitely small. Practically, this must be as small as possible. Any errors given by the non-zero size will be on the order dl, where d is the average diameter of the contact and l is the distance between the contacts. In addition to this, any leads from the contact should be constructed from the same batch of wire to minimize thermoelectric effects. For the same reason, all four contacts should be one same material. Geometry of the sample, as we can see, A is preferred to cloverleaf, B acceptable, square or rectangle contacts at the corners, and C not recommended, square or rectangle contact at the edge of the inside perimeter. Measuring definitions. The contacts are numbered from 1 to 4 in the counterclockwise order beginning at the top left contact. The current I12 is a positive DC current injected into contact 1 and taken at the contact 2 and measured in amperes. The voltage B34 is a DC voltage measured between contacts 3 and 4 with no externally. Applied magnetic field measured in volts. The resistivity P of the measure in ohms meters. The thickness of the sample T is a measure in meters, and the sheet resistance Rs is a measure in ohms per square. Resistivity measurements. Basic measurements. To make a measurements accurate is caused to flow along one edge of the sample, and the voltage across the positive edge is measured. From these two values, a resistance can be found using the own laws. In his paper, Van der Pauw showed that sheet resistance of the sample arbitrary shapes can be determined from two of these resistances. When measured along vertical edge is such as R 1, 2, 3, 4, and corresponding one measured along the horizontal edge such as R 2, 3, 4, 1. The actual sheet resistance is allowed related to the resistance Van der Pauw formula from Euler, as we can see, is equal 1. Reciprocal measurements and reverse polarity measurements. The reciprocity theorems tell us that R resistance ABCD equal resistance CDAB. Therefore, it is possible to obtain a more precise value of the resistance 1, 2, 3, 4 by making two additional measurements of the reciprocal values resistance 3, 4, 1, 2 and resistance 4, 1, 2, 3 and averaging the results. We define as the R vertical and the R horizontal. Then the Van der Pol formula becomes again Euler equal 1. For the reverse polarity measurements, a further improvement in the accuracy of the resistance values can be obtained by repeating the resistance measures after switching polarity of both the current source and the same portion of the sample. Using the opposite direction, the values of resistance vertical and resistance horizontal can be still calculated as the average on the standard of reverse polarity measurements. The benefit of doing this is that any of offset voltage, such as the thermoelectric potential and the feedback effect, will be cancelled out. Combining this method with the reciprocal measurements from both the formulas, resistance begins the R vertical and the R horizontal. The Hall measurements. When a charge, particularly such as an electron, is placed in a magnetic field, it experiences a Lorentz force proportional to the strength of the field and the velocity at which is traveling through it. These forces are strongest when the direction of motion is perpendicular to the direction of the magnetic field. In this case, the force of Lorentz is Fl Q B B. As we can see, Q is a charge, B is the velocity in the traveling as centimeters per second, and B the stretch of the magnetic field in cm. Note that centimeters are often used to measure the length in the semiconductor industry, which is why they are used instead of the SI units of meters. When a current is applied to a piece of semiconductor material, it results in a steady flow of electron stroke to the material. The velocity the electrons are traveling, as we can see here, and where n is the electron density, I is the cross-sectional area of the material, and Q the electromotive charge. If an external magnetic field is then applied perpendicular to the direction of current flow, then a resulting Lorentz force will cause the electrons to calculate and accumulate at one edge of the sample. Combining the above two equations and noting that Q is the charge on an electron results in a formula of Lorentz force experienced by electrons. This accumulation will create electric field across the material due to uneven electrons of charge, and is shown the figure. Finally, the magnitude of the Hall voltage is simply the strength of the electric field multiplied by the width of the material. That's it. Where T is the thickness of the material, since the seed density Ns is defined as the density of electrons multiplied by the thickness of the material. We can define the Hall voltage in terms of seed density. Final this formula. Calculations. First of all, the difference of the voltage for a positive and negative magnetic fields needs to be worked out. Voltage 1, 3, voltage 2, 4, voltage 3, 1, and voltage 4, 2. The overall Hall voltage is then this one. And the polarity of the Hall voltage indicates the type of material the sample is made of. If it is positive, the material is p-type, and if it is negative, the material is a n-type. The formula given in the background can be arranged